Okay, so this is number 1 in free response. And in this one, here's our acetic acid being titrated with NaOH. And we have a Ka and a pKa given. It says calculate the volume in milliliters of NaOH required to reach the equivalence point. And at the equivalence point, we know that the moles of acid are equal to the moles of the base. And if we use the molarity triangle, molarity equals moles divided by liters or volume, we could put and substitute for moles, molarity times volume of acid is equal to molarity times volume of base. And then we could put in our numbers right here and say that it's 0.5 molar, 10 milliliters of acid. It's 1 molar base, and to solve for the base at the equivalence point, we divide both sides by 1 molar, and 0.5 times 10 is 5 milliliters. So to significant digits, there'd be 5 milliliters at the equivalence point. Then, in letter B, we get a little bit more challenging. Calculate the pH of the acid before the titration is begun. And so we have acetic acid, and acetic acid is Ch16-17. When in doubt, react it with water because it's dissolved in water. It's a weak acid, so it's going to give away its proton to water and give you some H3O+, and then you're going to have some CH3COO Ch2 minus also remaining. Initially, we're told that the concentration of this is 0.5 molar. I'm just going to go to 1 sig fig so it's easier to write. None of this, none of this, none of this in the ice table. 0 of this to start with, 0 of this to start with. Now to find the pH, my goal is to find this guy. Because once I find that, then I can go on my pH square. Then I can go from H3O plus down here to pH. Now, to find out how much this is, I have to use my favorite letter from math class. So lose x, gain x, gain x. I'll end up with 0.5 minus x, x, and x. And so I end up with x squared divided by 0.5. Ignore this, say that it's small compared to 0.5. And that's equal to my Ka. And my Ka is given to me right here, which is 1.8 times 10 to the negative fifth. Multiply both sides by 0.5, and these cancel. Whoops, this cancels here, this does not. And then I have to square root this guy. So follow my calculator, and I have some people helping me with calculators as well, so if you could watch mine and make sure I don't make too many mistakes. Hopefully we'll get this right for the video. I got 0.003. Am I close for that for x? A couple other people got that. So 0.003 is equal to my H plus ion concentration, this thing right here. Now to find the pH, then I'd take the negative log of the 0.003, and if I do that on my calculator, negative log of my answer, I get the pH equaling 2.52 initially. Did anybody else get that? Are we pretty close with that? All right. So that's letter B. Now we get to the little bit more challenging ones where we actually add some base to it as well. So going on to letter C now. It says, calculate the pH when 1 milliliter of the 1 molar NaOH solution has been added. And so I'm given 1 milliliter of it, and initially I need to also know my moles of my acetic acid that started. So I'll be using the molarity triangle a lot here to find my number of moles, because your first ice table that you use when you're doing this has to be in moles. And so I'll write my equation to start with, and my equation is CH3COOH is being titrated with NaOH, and obviously the proton is going to go over here and connect to OH to give us water, and then we'll have the Na plus right here that is just a spectator, and then the CH3COO minus, that could be important because obviously that's the conjugate base, that's the other thing that's created right here. So my starting amounts have to be in moles, and so I have 0.005 moles of the acid to start with, where I do liters times the molarity times liters right here. And then I did the same thing for the NaOH, because it tells me that there's 1 milliliter, which is 0.001 liters, times my molarity, which is 1 molar. So I have 0.001 moles of NaOH to start with. And then there's none, none, none over here on the right-hand side to start with. Now when the change happens, I'll use up all of the smallest ones. So all of this will go away. So I will lose 0.001. I will lose 0.001. I will gain 0.001 over here. And then at the end, at equilibrium, or at the end of the stoichiometry part anyway, I'll do 0.005 minus 0.001, and I'll have 0.4 of the CH3COOH. I will have 0 of this left because it's all used up, and I will have 0.001 of this stuff created because it's a 1-to-1 ratio right here. Okay, now you have to be good looking. You already are good looking, but now you need to be good at looking. And notice that this is an acid, and this is the conjugate base. And an acid and conjugate base pair, when it's a weak acid, is called a buffer. And so you can find the pH at this point by using the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation, of course, is on your equation sheet, which is on the front of the test. And I'll point it out right here, it's in 2 different places. pH is equal to pKa plus the log of the base over the acid. And I've got it written out right here as well. So to find the pKa, we need to take the negative log of the Ka. I guess it does give us the pKa right here. It's 4.74, so that's what that's going to equal. And then we do the log of the base concentration, which is this, over the acid concentration. Now, I know we're in moles here right now. And to get to concentration, I would need to be moles divided by liters. And if I divided this by my total number of liters, you'll notice that I've added 1 milliliter of NaOH to 10 milliliters of this. And so I'd end up with 11 milliliters, which is 0.011 liters. But I'd also have to do that to this, divide it by 0.011 liters. And you'll notice that both of those would end up canceling out. And so it's actually just as easy to just take the ratio of the moles as it is to take the ratio of the concentrations. And then you also don't have to convert to the concentrations. So my math took 0.001 divided by 0.004, took the logarithm of that and added that to 4.74, and I got 4.14 here. Can somebody else do that on their calculator really quick? I got negative 0.602 for this log right here, and then added that negative to the 4.74. Confirmation on that one? Is that okay? Does the math look okay? Just didn't want to make a calculator error on the video here. Hopefully not anyway. Okay, we ready to go on to D? Okay, so letter D I think is maybe the toughest one. Calculate the pH when 5 milliliters of the 1 molar NaOH has been added. So here we are with the same equation. And this time in our ice table, we'll once again go to moles. So start with moles right here. And remember, I got the 0.005 by doing the molarity times the liters for the acetic acid, molarity times liters. Whoops, molarity times the liters right here. And then I did the same thing for the NaOH. It's 1 molar, and there are 5 milliliters, so I got 0.005. 000. Okay? Now I will lose the smaller one. And of course, they're the same. So I'll lose 0.005, I'll lose 0.005, and I'll gain 0.005 over here. And so in the end, I end up with none of the acid, none of the base, and I end up with 0.005 moles of this conjugate base right here. And of course, I get 0.005 of water and 0.005 of Na+, but those don't affect the pH at all, because they're just neutral in solution. This is from a strong base, and water, of course, it doesn't affect the pH. So, my next step is to recognize that this, the only thing left that affects the pH, is a weak base. And to find the pH of a weak base by itself, I need the concentration of it. And so I will take the moles and divide it by my total number of liters. This is the molarity triangle once again. So my moles divided by my total number of liters, which is 5 milliliters plus my 10 that I started with, 0.015 right here. 15 milliliters total solution. The other thing that I'll need, now that I recognize this is a weak base, is I'll need the Kb the Kb. So I'm given the Ka right here is 1.8 times 10 to the negative fifth, and I know that Ka times Kb is equal to 1 times 10 to the negative 14th. And so if you have this, if you don't have this on your pH square, you know this is true right here. And now I'm going to solve for Kb. And so solving this for Kb gives me 5.55 times 10 to the negative 10th for the Kb of this stuff right here. Here's my molarity after I do this division, 0.005 divided by 0.015. Can I get a confirmation on that? Did you guys do that? 0.005 divided by 0.015. Do you get 0.333 molar? Okay. So there's my molarity of my base. Now I have to do the dreaded second ice table. And so on this one, I take my weak base. When in doubt, react it with water. It's going to be a proton acceptor and get one more, and it's going to make some OH minus. And this guy's the key. This is the ticket right here to get me into the pH square, and then I can go here and here to find the pH, which is ultimately what I want to have. So now it's a problem that we learned a chapter ago. Here's my initial concentration, 0.3333 molar. None, none, none. Lose x, gain x, gain x. 0.033 minus x, x, and x. Ignore this x and say it's small. Take these x's, put them on the top, divide by 0.3333, and set that equal to the Kb. That's why I needed the Kb up here, because this is acting as a base, because it's going from left to right, accepting a proton. Now, multiply both sides by 0.333, take the square root of those sides. I got x to be 1.3 times 10 to the negative fifth. Can I get a confirmation on that? To multiply this by 3.333 and square root it to get 1.36 times 10 to the negative fifth? I got one confirmation on that. Okay? Now this gives me my OH minus, and I'm in the pH square. Negative log that to get POH, subtract from 14, and so I got POH is 4.866, subtract from 14, I got a pH of 9.13 at the equivalence point. So notice equal moles here, called the equivalence point, does not necessarily mean a pH of 7 because we have some of this conjugate base present there. We okay with that one? Longest problem in the book right there. Last problem is letter E. Letter E says calculate the pH when 5.5 milliliters of the 1 molar NaOH have been added. So here's my same equilibrium. Ice table. Moles. So once again I do molarity times my liters. And I have 0.0055 moles of the NaOH now. None, none, none. Lose the smallest, which is 0.005. Lose the smallest. Gain the smallest over here. And then I end up with none of the acid left, some of this NaOH left, and some of this CH3COO minus left. And once again, you need to be good at looking. You're already good looking, now you need to be good at looking. And so you notice I have a strong base remaining, and I have a weak base that I created. Now, if I told you there's a strong base and a weak base, which one would affect the pH? Hopefully you'd pick the strong one. The strong base determines the pH much more than the weak base. Therefore, you ignore the weak base and find the pH just using the pH square. So you have this remaining right here. The only difficult thing you have to do is remember, divide it by the liters to get the molarity. Because you have to have the concentration of OH minus, because this is OH minus is moles. So take your moles, divide it by your total number of liters, which is 5.5. plus 10, so 0.0155 liters. That gives me my molarity of my OH minus right here that came from NaOH. Now you're in the pH square, so negative log that, and you get 1.49. That's the POH. subtract that from 14, and you get 12.2 for the pH. Is the math okay there? Did somebody try it? A couple of the pieces along the way? Did it work? I'm thinking so. I don't see too much objection. All right, so there's the super big long one. There'll be several parts of that on the test in the near future. Thank you.